Hi, this is Giovanni da Prat, and welcome to Example 3 presentation. Example 3 deals with a homogeneous gas condensate reservoir, and the well is slanted well. Objectives are, besides the reservoir parameters determination, we want to know the gas deliverability for future sales and skin components. Being a gas condensate and being slanted, you may expect that we have two different skins, one probably depending on rate, and the other depending on if it is the length, the perforated length here has some damage. Okay, regarding reservoir and well data, we have a reservoir with 3,000 psi initial and a thickness of 250 feet, quite a good thickness. Other parameters are like well radius and porosity, 15%, and the well is slanted and the degree with the vertical is about 50 degrees. Regarding fluid data, this is the specific gas gravity, the condensate gas ratio, about 30.8 stock-ton barrel per million cubic feet, and temperature and other related parameters to the fluid, like the compressibility. These rates were measured from separators. It means that this is it has been a DST type of test. In addition, because we have two phases here, we're dealing with a gas condensate, then we need to enter the relative permeability in the game, which with the software is quite, you can do it as long as you know the curves, the relative permeability curve. Okay, here is our test history, and what we see here are the bottom hole pressures and the rates. In this case, we're showing the liquid rates and the gas rates. We have this trend here, which looks like it is like a modified isochronous type of test commonly done in gas. And even though the transmissibility is quite good here, we decided to have an extended production period just to make sure that we reach limits. And to do that, besides the advantage of confirming some model, there is also the need to have a gas deliverability curve, which is not transient, rather stable, because you reach the limit and your absolute open flow potential is more practical. Okay, first thing to do is we're going to make a log-log diagnostic plot of all the events to see what we can, to have a feeling of what type of reservoir is. So this is all the events, and now let's go by flow regimes. This is wellbore storage transition. This part here is due to the slanted well effect. We'll see later on with when we do some sensitivities that this could, this level here could be even higher depending on the degree, the deviation degree. The more higher this level will be. Then here there is radial flow type of regime, but very short in time because limits are starting affecting the pressure, as we can see here. These are the build-ups, and you can see that the build-up reach stabilization. I mean, you reach the static pressure, and the drawdowns, if that confirms what a ceiling boundary is and not a constant pressure boundary. You may say that because the buildup is going down, there is some kind of active boundary, constant pressure like a huge aquifer. But when you do the drawdown is confirming that it's not dealing with pressure maintenance. It's rather is a ceiling type of boundary. And this is the extended production period, which adds or confirms in a way where this tendency will go if we have more time during the drawdown, the short drawdowns. And you can see here there is a tendency of going for the derivative, to develop a 1 unit slope classical of a pseudo-steady state. So from this, well, more practically speaking, or visually speaking, from this on, this is a ceiling boundary type of effect. It's not a fault, it's not a discontinuity, because it's confirmed by this tendency here. Okay, even in the previous slide, you realize that our different build-ups, and when we look at the separation of the change in pressure to the derivative, which is the same for all of them, but the vertical separation is different. It means that as we may expect, there is a skin dependence on rate effect here. So if that's the case, what you do now is to identify, to find the effective skin for each of the drawdowns periods through the build-up analysis, and build the skin versus rate plot. And from this plot, you may have an idea of your turbulence constant, which is this one here, about 0.00225. And also, what is your skin at laminar or mechanical skin that you get it from this graph here when you extrapolate to zero flow rate. Okay, so now what we do is to simulate, we go to the classical simulation using nonlinear regression, and after several tries, we end up with a model that simulates, in this case we're showing just the last build-up simulation, which simulates quite well. And this, the results you can see here from the well and wellbore. Later on I show you from the reservoir parameters. But important is a skin of 20, which is the laminar. But you got a geometrical skin of 2.7 due to slanted, then a huge turbulent constant, and other parameters probably you already know, like the deviation is 50. If you can even play with the deviation, like a well, which is a limited entry, and then according to you can have the information about what is the perforated interval. If you want to leave that open to regress, you may leave this open, and then probably you find out a different value. But this is a hard, let's say, hard information that it's not, we decided not become variable, because that is found by the well data, drilling well data. So here, just I put for comparison what is the effect of this deviation angle. One effect is that if you're not aware of that, you may end up saying that this is radial flow for the formation, which you can see here is a transition. It's not radial flow. It's just going a transition to radial flow deformation is around here, probably. Not probably, we don't see visually okay, because the limit affects immediately, almost immediately, in less than 10 hours, because the high transmissibility. So here you can see this is for 0 degree, our well is vertical, and the other parameters is 90 degree, our well is completely horizontal. You can see the difference. And in the middle of these two extreme values, well, in our case is this one here, which is 50. this is about 60 or 70 degrees. So the important thing here to recognize that the well is deviated, let's say important deviation, probably 10 degrees or 15 degrees, that's nothing, it's around here. But if it is more like 50, like the one we have, you can see here the importance of recognizing that this is not radial flow deformation. Radial flow is over here. If you compute radial flow here, you end up with a value of permeability less than the one that should be. So one point important to do in any interpretation is to make sure that you simulate the whole pressure test of the history, like in this case. This is your data, and you can see the simulation results. And also you can draw here if you want to see the tendency of the reservoir pressure. So in addition to the values already mentioned before about the well and completion, here you can see the equivalent permeability dealing with gas and condensate, which is 110. And this is a result about the anisotropy caused by the well being slanted. And relevant here about these parameters, we're talking about the 1,000 feet distance, which is quite a short distance. Okay, this is the gas deliverability, or the IPR plot. Here, you can get an idea of your absolute open flow potential, which is 90 million, but remember, the well is damaged, and this could be, if you decide to remove the damage, this could be higher than the one shown here. N is an exponent which is 0.557. It means quite a high turbulence effect, which we already mentioned before. If you extend, by extended, here we mean this curve here, the result from this curve, which is more stabilized condition than this one here. And you're going to have probably a 85, and again remember, this has a damage we already mentioned before. By removing that damage, you can play with nodal analysis. You can see the effects on your AOA. Okay. So this is the influx. This is the input for a nodal analysis. Let's say you have a pressure drop of 500 psi. You may end up with a value of 40 million standard cubic feet per day, but you have to make the other component, the tubing performance, to know which exactly the rate is going to be, your production rate for that well and its production components. But this is the starting from the nodal analysis. This is the same plot before, but made in Cartesian scales. So in conclusions, evaluation objectives were successfully accomplished. This is, normally used to say this because in wells, when you do the test, you have some objectives and then you would like to accomplish them. So this was done here. I have been in many field cases, and what happened many times is that the test is not going where it is supposed to go, and because of contingencies. Therefore, you need to deal and manage contingencies to get your objectives. In this case, was okay. And you need to determine the skin components, especially for gas, because you're going to have a component very important here, which is the turbulence. And this turbulence is, if you compare it with the total skin, is quite representative. I mean, the the slanted well component is not as big as the turbulence skin component. And here some for you to know some equations that are used in the case of a slanted well. And these skin components always sometimes refer to the skin for a vertical well. And this is the component for the turbulence. Now, what we're going to do now is to use the software and recreate this, the results. So here is as we start, this is a Sapphire, which is version over here 5.20. Nowadays there is a updated version. So what we do here is we have our pressure and rates and other inputs parameters we're not going to show you, like you have a multi-phase, you got here, just show you for completeness, you got your gas and oil properties, you want to see the dew point, it's over here. So all this, same for relative permeability. So these things you input. And initial or general information about the pay zone and porosity, as I showed here. So what I want to recreate here, what has been presented. So first thing to do is to extract, and in this case we're going to put all together like I did before, all events. We can do like this thing here. And here you have it in a glance, let's say, some idea for you that gives you an idea of your reservoir. And if you're quite experienced, give you an idea of which model will better fit the results. This is in, let's say here, tools. Let's leave it infinite here for a moment. Okay. With this software, one thing that you can do is that you can, using these tools, as we will see later, is going to help you to recognize also you can get some initial estimates of your drainage area or this one here, for instance, this level, it allows you to get, without doing any simulation, to get your permeability thickness product. I'm just putting as an example. Because here the software needs these values here to start the regressions with other models. But here you got already that the equivalent permeabilities are around 100 millidarcy and other parameters. Okay. Okay. So let's go now back again, and now to make the skin versus rate plot, we're going to use only the build-up data, or you can use only the drawdown data, but let's make it simple. Let's use only the build-up data. What I was trying to say that you can use this drawdown data, and you're going to have the same results. So now this is what you got here, and then to compute the skin, the relationship between skin and rate, you can come to multiple lines, and you can over here identify where the radial flow is, then what it does is automatically computing the skin for each from any of these lobes. You're going to have the skin, effective skin, and after, for instance, here is 87, from the other build-up is 127. That all comes from this classical calculation. And you end up with this curve here, plot skin versus rate. And the idea is to get this value here. What is your turbulence constant, which is 0.002, because you need it now when you do the modeling. So let's now let's simulate our test. We're going to use the last build-up only. We can use all of three, but just for you to show, I can show you better using one. So here, let's go here. Now we're going to look for the model that can simulate this data. So what we can see here is first there is a slanted component, there is a radial flow, and then there is a decrease. Pressure derivative is decreasing. It means that it's stabilizing. That could be due either to a constant pressure limit, quite strong, or to a ceiling, a volumetric reservoir. So you have here some tools, and in the tools you see that the Weber storage is constant, and then you can choose a closed circle, and here it appears this, let's say, tool that helps you to see where, it takes some time to move it. Okay, and you go down a little bit. By doing this, we're not going to stay very much here. But you see here, you already got this simulation here, and before doing the whole simulation, you can have the results. In this case, that the boundary is a circle, closed boundary, and your radius of that limit, of that sealed boundary is about 967. So with all that in mind, you need now to do the simulation of the whole test, and then you come here to we can use either analytical or numerical. Let's use analytical, and then here we have to specify that there is a ray-dependent scheme, like we do here, and here you need to tell what you got before, which is related to the S to dq, that value for the turbulence constant, which was about 0.02 approximately. And so now you try to make the match, and this is an initial. Now you can refine a little bit that one. Oh, because I forgot, I'm sorry, I forgot to tell the software that I have a deviate, a slanted web. So now we put here the degrees, 50 degrees, and now we'll do again now. And you can see now it's better. So you can improve, if you like. It's not needed here, because mainly what I wanted to show you how to get the result from. But in practice, if you like, you can improve it. You feel that you need a better match. The thing is that in this case, we hope it is very fast to do it. some cases, depending on which type of condition you have, especially you have, oops, we see here that for some reason it's not good. So let's go back here and some value, which is here the perforated length was something I missed, 250, and the thickness is to be 250. Yeah, when it happened when I did the improvement, maybe I leave some parameters which are constant, I leave them in regression. I did not realize that. Well, this is, I'm doing it in real time now. Okay, hope now we're going to get a better match. Now we go to improve again, and in this case, I say skin HW, this we want not let him to improve, and let's see now if we got a better value. Let's say that we use all this as a target. And as I said, this is, I did it before, so if I don't get it here, it's just like I would like to know you what the situation is sometimes with this type of regression. Okay. It's getting 100. Let's stop here. Okay, here you have now a better. Let's take out the tools. Here you can show tools, no tools. Okay, and so that's the way you got your results. Here you can see the match. Probably need more refining here, but this is what you normally do. Here is the one I did already before, and that's the one you have in the. I just wanted to do it with you, what I did before with patience and more time. Okay, so I would like to thank you for your time, and again, as I said, probably I'm telling you in the other examples. If you have any doubts or questions you want to share, feel free anytime to contact me via WhatsApp or via email. Thank you very much again, and hope to see you in example 4.